Potential dividers. Here we have a simple circuit with two resistors in series. We have a 12 volt DC supply and a voltmeter reading the potential difference across the bottom resistor. Now the potential difference is shared between these two resistors, and so if they are both of value 5 ohms, they will take half of the 12 volts each, and this voltmeter would read 6 volts. If we changed both resistors to resistors of 10 ohms each, the potential difference would still be equally shared between the two, and so this voltmeter would still read 6 volts. But now a lower current will flow in the circuit, and so the internal resistance of the power supply will be less significant. Changing the resistors again to a 5 ohm resistor at the top and the voltmeter reading across a 10 ohm resistor, this part of the circuit now has twice the resistance of this part. So it will take twice as much of the potential difference as this, and that will lead to a voltmeter reading of 8 volts, as there will now be 4 volts across the 5 ohm resistor, leaving 8 volts across the 10 ohm resistor. Having the resistors the other way round, with the 5 ohm resistor at the bottom, this would now take half the potential difference of this one. The voltmeter would now read 4 volts. Picking values of 10 ohms for the top resistor and 50 for the bottom resistor, now the voltmeter will read 5 times the potential difference across this resistor as we have across this resistor. So this will take 5/6 of 12 volts, while this one takes 1/6, and so the voltmeter will now read 10 volts. Again swapping the resistors round, so we now have the 10 ohm resistor at the bottom, which takes 1/6 of the 12 volt supply. The voltmeter will now read 2 volts. Now let's look at the general case, where the potential difference of the supply I've called V in, the input potential difference, the resistors R1, over which we read the output potential difference, and R2, the other resistor. And then this will give VO, our output potential difference. Now this is just the share of the total potential difference, and so we find that VO is given by resistor 1, the resistor it is placed over, divided by the total resistance, resistor 1 plus resistor 2 in this circuit, multiplied by the input potential difference. That formula covers the case of two resistors, R1 and R2, but we can also say that VO, the output potential difference, is equal to the resistor over which we measure the output potential difference, divided by the total resistance, multiplied by the potential difference of the supply. A sliding potentiometer can be used to give any output potential difference between 0 and the total potential difference of the supply. In this case we have a length of resistance wire, this is often coiled, across part of which is a voltmeter measuring the output potential difference. Now the total potential difference of the supply will be lost steadily across this resistance wire, and at the moment the voltmeter is measuring this percentage of it. In this case the output potential difference will be roughly half the total potential difference. If we read the potential difference across more of the resistance wire, the output potential difference will increase. We're taking a bigger share of the input potential difference. And here the output potential difference is reduced, as we're only measuring across about a quarter of the length of resistance wire. so we would read about 25% of the supply potential difference. It's often more convenient to have a control which is turned rather than slid, and this is the arrangement that provides that facility. It's basically the same circuit as we had before, with the supply potential difference sending a current round here, but now we can tap off at this point and across our voltmeter. As the sliding contact is moved in this direction, the voltmeter will read a greater proportion of the input potential difference, and so V0 will rise. We can use a potential divider to produce a temperature-dependent circuit. In this case, we have a thermistor as our lower resistor. Now with a thermistor, as the temperature rises, its resistance falls, and so the voltmeter will steadily read a reduced share of the input voltage. So, as the temperature rises, the resistance of the thermistor falls, its share of the potential difference falls, and that leads to a lower output potential difference, V0. Now I've swapped the resistors, so we have the fixed resistor down here and the thermistor in the top position. As the temperature rises, its resistance again will fall, and so its share of the supply potential difference will fall. In turn, the fixed resistor will take a bigger share of the supply voltage, and V0 will rise. So just to stress again, with the thermistor in this position, a rise in temperature gives a higher output potential difference. In the previous case, with the thermistor down here, a rise in temperature gave a drop in output potential difference.